Hello, I would like to introduce our work, Depth from Asymmetric Frame-Event Stereo, a divide-and-conquer approach. This work is jointly done in University of Science and Technology of China, by Xihao Chen, Wenming Weng, Yueyi Zhang, and Zhiwei Xiong. Depth sensing is one of the most crucial abilities in the evolutionary process for humans, and this mechanism relies on human stereo vision. To simulate human stereo vision, machine stereo vision was first proposed in the 1960s. Machine stereo vision employs a dual camera system to capture images of the external world from different perspectives, which are then processed by the system's back-end units to perceive depth. The emergence of machine stereo vision has also led to the development of numerous related applications. For example, the onboard assisted driver systems in the field of autonomous driving, obstacle avoidance systems in the drone field, and scene-based three-dimensional scanning systems. To better estimate disparity and calculate depth, we often use a symmetrical dual camera system for image acquisition. That is, the cameras for the left and right perspectives have the same lenses, sensors, ISPs, image signal processors, and employ the same optical and exposure settings, ultimately producing symmetric stereo images. This design aims to both closely mimic human stereo vision and minimize the difficulty in stereo matching for estimating disparities. Although symmetrical stereo systems have many advantages, the stereo images captured by symmetrical systems have high redundancy, hence gradually failing to meet the demands in production and daily life. Asymmetric dual camera systems have begun to be proposed and deployed in various devices. For instance, the telewide camera system equipped in smartphones, and the color event camera system used in autonomous vehicles. Event cameras asynchronously measure brightness changes in a scene without motion blur or saturation, while frame cameras capture images with dense intensity and fine details at a fixed rate. The exclusive advantages of the two modalities make depth estimation from stereo asymmetric frame-event, SAFE, systems appealing. However, due to the inevitable information absence of one modality in certain challenging regions, existing stereo matching methods lose efficacy for asymmetric inputs from SAFE systems. To understand this system, let's first discuss the complementarity between the color camera and the event camera. Generally, the event camera only outputs sparse event signals, while the color camera can output dense intensity signals. In static/smooth regions, the event camera has no output, whereas the color camera can output rich textures or dense intensity. In high-speed, high-dynamic range regions, the event camera can produce high-quality event signals, while the output from the color camera might suffer from blurriness, overflow, and other quality issues. Therefore, it is evident that color cameras and event cameras exhibit strong complementarity. Our paper proposes a divide-and-conquer strategy to fully utilize the complementarity of two modal signals. The imaging scene is divided into regular and challenging regions. Regular regions refer to regions where both the color camera and event camera produce high-quality signal outputs from their perspectives. For example, in the image, areas with slow-moving objects like workers and water tanks fall into this category. Color images typically exhibit high-quality color intensity output in these areas, and a substantial amount of event signals can be triggered, enabling a good estimation of correspondence between left and right views. Therefore, for such regular regions, the cross-modality stereo matching between color and event signals is chosen for depth estimation. The challenging region refers to regions where, between the two modalities of color and event signals, the camera system can only capture one of these modalities, leading to information loss and highly asymmetric modalities. For instance, in typical scenarios, a color camera can capture various information such as color, brightness, and texture, while an event camera can only output high-quality signals in the contours of objects, with no event signals triggered in the physical interiors. In challenging lighting conditions, the event camera maintained its high-quality output while the color camera faced serious overexposure issues. For these challenging areas, this paper used a motion recovery framework based on single modal signals to estimate depth. This is because, for a properly functioning modality, there exist high-quality signals in both of its two different temporal views. For instance, in the event camera modality capturing high dynamic range scenes, areas such as cables, trees, and railings marked by the green box exhibit high-quality event signal outputs at different time frames. Therefore, we can utilize the correspondence between two consecutive views in the event modality to estimate the depth of these regions. As aforementioned, to enable robust stereo depth estimation in challenging regions by utilizing the complementary information of safe systems, we explicitly decompose the task into three branches, including frame-event stereo matching, which conducts stereo matching using a reference intensity view and a source event view. Event-based structure from motion. With two source event views, it could be recognized as a two-view SFM problem with known camera poses. Frame-based structure from motion, which is similar to the above but uses two source frame views. Since different subtasks have different reference images, we propose a dual sampling strategy to fuse different subtasks. Instead of reprojecting and merging the depth estimates of different subtasks, we fuse their aggregated cost volumes, which are deliberately aligned in terms of both spatial locations and depth hypotheses. In the strategy, the cost volumes of different subtasks are all constructed in the spatial locations and depth hypothesis planes of the same reference view. Specifically, to fuse the subtask that does not involve the reference view, we dual sample pairs of candidates from two source views with the locations and depth planes of the reference view to construct a cost volume aligned to the others. The dual sampling strategy intuitively works for most regions without occlusion. In regions with occlusion, there are pseudo-matched candidate pairs to interfere with depth estimation. Specifically, although these pseudo-matched candidate pairs indeed reveal the exact geometry of certain 3D scene points, e.g., the yellow star and the blue triangle, they cannot infer the ground truth depth for the reference view since the 3D scene points they represent are occluded by the scene points closer to the reference camera plane, e.g., the green circle. In this way, the depth probability distributions in these regions are inherently multimodal and may not indicate the correct depth. To address this issue, we propose a temporal fusion scheme to utilize the long-term sequential inputs of safe systems given that currently occluded regions might be matched in previous time steps. Instead of explicitly propagating the previously estimated depth, we choose to propagate the intermediate features of different branches at the previous time step t-1 to those at the current time step t by CONVLSTM cells. Quantitative result. Table 1 shows the quantitative results of different methods on the DSEC datasets. Among the methods from the first category, PSMNet demonstrates the best performance. The performance of the second category degrades severely since the E2VID framework loses efficacy and generates unsatisfactory intensity images, exacerbating the difficulty of matching. For the third category, HDES does not construct cost volume to capture correspondence and thus presents inferior performance, while DCNet obtains negligible improvements over PSMNet, indicating that the asymmetry caused by the information absence of a certain modality cannot be mitigated by the edge maps. In contrast, our method introduces SFM subtasks to estimate reliable depth from two consecutive views with the same functioning modality, thus outperforming all comparison methods by a large margin in all metrics. The visual results of one exemplar scene is shown here. In these scenes, comparison methods that only rely on the inputs at the current time steps cannot present the correct disparity, since a certain modality fails to report high-quality signals in some challenging regions, e.g., the railing and the trunks in the first scene for event cameras and the chains in the second one for frame cameras. In contrast, our method obtains more robust results, indicating the effectiveness of our divide-and-conquer approach that solves these regions by SFM subtasks. Here is a visual comparison of safe systems with stereo-symmetric event-based EEDDSE and frame-based FFPSMNet systems. Our method estimates robust depth in various scenarios while the others fail in certain scenarios, e.g., EEDDSE in the flickering light region and FFPSMNet in the low light region. Contributions of this paper are summarized as follows: a novel divide-and-conquer approach to adequately utilize the complementary characteristics of safe systems. A dual sampling strategy to fuse different subtasks at the cost-volume level without reprojection. The SOTA performance of asymmetric frame event depth estimation on the DSEC dataset. Thanks for your attention.